Today I'll discuss one of the most important topics in physical chemistry, that is gas law. We'll look at the ideal gas law. Here we will discuss the ideal gas law like PV is equal to inerty, and then we'll discuss partial pressure, and then finally we will discuss real gas behavior. So here I'll give 8 comprehensive examples. One, that volume and temperature calculation, then partial pressure analysis and real gas deviation, and then compressibility analysis. Now first, ideal gas law. We know that ideal gas law is nothing but PV is equal to inerty. So here we can rearrange that ideal gas like V is equal to nRT by P here, and T is equal to PV by nR, and P is equal to nRT by V. Here R is equal to, let's say, liter, atmosphere, mole and Kelvin. So here V is suppose in liter, unit of V is liter, and T is in Kelvin, pressure in atm, and N is number of mole. So R is here 0.08206 liter atm per mole Kelvin. And rearrangement already I told that V is equal to nRT by P, T is equal to PV by nR, P is equal to nRT by V. Now first example, volume calculation. PV is equal to nRT application. So first problem is calculate volume of 2.5 mole of carbon dioxide at 25 degrees centigrade and 1.2 atm. So now here N is given, that is 2.5 mole of carbon dioxide. T is also given, that is 25 degrees centigrade. We have to convert in Kelvin. So that is 298.15 Kelvin. Pressure is given, that is 1.2 atm. So R is, we already know that 0.08206 liter atm per mole Kelvin. Now we know that PV is equal to nRT. If we rearrange, V is nothing but nRT by P. Now if I plug all these values, that N is equal to 2.5 multiplied with R 0.08206 multiplied with T 298.15 divided by P 1.2. So finally we will get V is nothing but 51.00 liter, means 51 liter. So now here key learning is always convert temperature to Kelvin before the calculation. Okay, fine. So here we did that. Next is temperature calculation, PV is equal to nRT application. So here is the problem statement, find temperature of 1.5 mole N2 in 30 liter at 0.8 atm. Now given N is given 1.5 mole nitrogen, B is given 30 liter, P is given 0.8 atm. Now here that from that PV is equal to nRT, if we rearrange that T is equal to PV by nR. So here we plug that P is 0.8, then V is 30 liter, and then N is 1.5 mole, and R value is 0.08206. Now if we do the calculation, we'll get T is equal to 194.88 Kelvin. So here temperature conversion, so T degree centigrade to T Kelvin, so that will be minus 273.15. So now if I can convert this Kelvin to degree centigrade, we have to subtract 273.15. So finally T will be minus 78.27 degrees centigrade. So here very low temperature, it is a minus, very low temperature indicates extreme condition. Now next example, Dalton law of the partial pressure. So that principle of the Dalton's law is, in gas mixture each component exert pressure independently. So P total will be P1 plus P2 plus P3 plus ... plus Pn. So here 1, 2, 3 are nothing but the component. So partial pressure I means I component is nothing but Xi. Xi is the mole fraction into P total. So here Xi is nothing but Ni by N total. So for critical for gas mixture, atmospheric chemistry and that industrial process. So these are the area we can use the mole fraction. So now here is the example, partial pressure calculation. So gas mixture, so gas in a gas mixture, so in that gas mixture, so what are the component? Nitrogen, oxygen. Okay, so here 2 mole of nitrogen, so 1 mole of oxygen, and 0.5 mole argon is there. at 300 Kelvin and 10 liter. So now here, so partial pressure we can calculate. So P is equal to N at T by V. So N is 2 mole for nitrogen, then R we know 0.08206, T is 300 Kelvin and V is 10 liter. So that will be 4.926 atm. Partial pressure of that oxygen. So say similar way we can do that. P is equal to N at T by V. So P, that 1 mole, then R 0.08206 into 300 by 10. So that is 2.46 atm. And that argon pressure, that P is N at T by V. So P is nothing but N is 0.5, then R, and then T by V. So that is 1.232 atm. So now here total pressure and mole fraction. So total pressure is here 4.926 atm plus 2.463 plus 1.223 atm. So if I add all these 3 atm pressure, so that will be 8.621 atm. Now here mole fraction will be 2 by 3.5. Why 2 by 3.5? So you have to see here. So xi is nothing but that pi by p total. So here that p by 3.5. okay, so here that mole fraction is that individual mole by total mole, so 2 by 3.5. so here you can see here one way you can do that calculation. Xi is pi by p total, or here xi by ni by n total. That way also you can do that. So now here, so individual mole by total mole, individual mole is 2 and total mole is 2 plus 1 plus 0.5. so 2 by 3.5, that is 0.571, and that mole fraction of oxygen is 1 by 3.5, that is 0.286, and X argon means mole fraction of argon is 0.5 by 3.5, so that is 0.143. So now I'll talk about real gas behavior. So here a reality check. The real gas deviate from ideal behavior due to the molecular size and intermolecular force. So van der Waals equation, that P plus AN square by V minus NB by nRT. So A is account for intermolecular attraction and B is accounts for molecular volume. So now here if I rearrange that van der Waals equation, so that will be P is equal to nRT by V minus NB minus AN square by V square. So two correction terms modify the ideal pressure. So now here for carbon dioxide, A is given 3.640 atm liter square mole square by mole square, and B is 0.04267 liter by mole. Okay, so for carbon dioxide that A and B is given. Now here is the one example. Compare real gas versus ideal gas pressure 2 mole carbon dioxide at 300 Kelvin in 5 liter. So now here van der Waals real gas van der Waals equation. So P is equal to nRT by V minus NB minus AN square by B square. So now first term we can plug that N is 2, R 0.08206, T is 300, and V is that 5 liter minus 2, that is mole, and B value already given in the last slide, so 0.04267. so that will be the first term, and if we do the calculation, that will be 10.014 atm. And second term, that is AN square by V square. So A value is 3.640 into 2 whole square by 5 square, so that is 0.582 atm. So P real, so 10 minus 0.14 minus 0.582, that will be 9.43 atm. And ideal gas, so P is equal to nRT by V. If we plug N is equal to 2, R is equal to 0.08206 into 300 divided by 5. So P ideal is 9.852 atm. So ideal gas overestimate pressure by 4.5%. So P ideal is 9.852, P real is 9.432. So that is our ideal gas overestimate pressure by 4.5%. So key insight, real gas show lower pressure due to the intermolecular attraction. So next is example is the compressibility factor analysis. So compressibility factor, quantifies deviation from ideal gas behavior. So Z is equal to PV by nRT. So Z, when Z is equal to 1, that is perfect gas behavior. Z less than 1, attractive force dominate. So here molecule are very closer, and Z greater than 1, repulsive force dominate, means molecules go away. So now for carbon dioxide example calculation, so we know that P real is 9.432 atm. Okay, and then if I plug that PV is equal to nRT, so P is 9.432 and that V is 5 liter, then N is 2 and R is 0.08206 into 300 is T. So after doing the calculation we will get Z is equal to 0.958. Okay, so means Z less than 1, confirm attractive force dominant for the carbon dioxide under this condition. So that way we can easily calculate the compressibility factor. Now here, so ideal gas volume 2.5 mole carbon dioxide, 2.5 degree centigrade and 1 atm. We can use V is equal to nRT by P. So result is 51 liter. So temperature conversion crucial. Then ideal gas temperature, so PT is equal to PV by nR. Okay, so 1.5 mole nitrogen, 30 liter and 0.8 atm. If we plug, then we'll get 194.88 Kelvin. So that is minus 78.27 degree centigrade. So always convert to Kelvin. Okay, and partial pressure into 2 mole of nitrogen, 300 Kelvin, 10 liters of P is equal to nRT by V. So that is 4.926 atm. Then van der Waals gas, that is real gas. So if we for the given condition 2 mole carbon dioxide, 300 Kelvin and 5 liter. Okay, and we know for carbon dioxide the A and B value. If I plug that, we will get 9.432 atm. And compressive factor we calculate for carbon dioxide example above. So Z is equal to P by nRT, so that is 0.958. So Z less than 1 indicates